This will be I think, short video on kind of completing the idea of quadratic interpolation. So what we did last time is we found the quadratic polynomial between the points 0, 2, 1, 3, and 2, 5. And so I want to kind of continue that and show how you take the next step if you're trying to build a quadratic polynomial interpolation of an entire data set. Okay? So I've got here an expanded data set. It's got those 3 points, 0, 2, 1, 3, 2, 5, and then 2, 5, 3, 2, 4, 1. 3, 2, and 4, 1 have been added on. And so we've got 5 points total. And so I want to show you how you can do a polynomial interpolation moving on. Okay? So the key thing here is that while you do want to do these in sets of 3, right, you need 3 points to get a quadratic polynomial, you want them to overlap by 1 point. Okay? So we're going to have a quadratic polynomial that goes between these 3 points, but then we're going to have a quadratic polynomial that goes between these 3 points next. Okay? And that's going to be the best parabola through these points, which is going to look like this, which isn't terribly satisfying. We'll talk about that in a minute. And so what you do is you go through and you can construct that polynomial the same way that we did the Lagrange polynomial for the other one, right? So you can go through and say y equals x minus 3, x minus 4. So we're skipping this 2, 5, 2 minus 3, 2 minus 4, and multiply that times y equals 5, right? So since we're skipping that point, we use that y value. And then we've got skipping this one, x minus 2, x minus 4, over 3 minus 2, 3 minus 4, times 2, and then the last one, skipping this last point, x minus 2, x minus 3, over 4 minus 2, 4 minus 3, times the y value for that last point, y equals 1. Okay? And so if you go through and simplify this out, you can multiply all of this out. Surprisingly, this comes down to the very lovely polynomial x squared minus 8x plus 17. It's kind of a little bit of algebra to get there, but it's actually not that bad. So again, to kind of work these out, the top piece here you can just FOIL out, multiply out these two pieces. This becomes a single constant, and so you've got a polynomial. In this case, x minus 3 times x minus 4 gives you x squared minus 7x plus 12, multiplied by a number. All of this gives you a number. In this case, it's 5 over 2, 5 halves. And so you've got 5 halves times this polynomial. This one becomes negative 2 times this polynomial. And it actually isn't that much work to kind of break this down into an actual polynomial. So what we get for our final quadratic interpolation is on 0 to 2, we're going to use 1/2 x squared plus 1/2 x plus 2. And then on 2 less than x less than or equal to 4, we're going to use x squared minus 8x plus 17. Okay? And you'll notice here I'm not very careful about whether 2 is included in the first one or in the second one. Both of these go through the point 2, 5, so they match up at that point. Okay? Now, when you get this interpolation, it looks like this. And while this is good, and it can give you the values in between, it's not terrifically satisfying because we've got these kind of sharp points in our graph, these discontinuities, places where the function, the piecewise function, isn't differentiable. Okay? So if you've got some place like this where you've got no derivative, it doesn't really look like a model function. Okay? And so one alternative to doing something like quadratic or cubic interpolation is to use what's called a spline. Okay? So I'm not actually going to go through the mathematics of this. It's very complicated. We talk about it in other courses. You can do it in Excel very easily. So a spline, and specifically a quadratic or a cubic, usually we talk about a cubic spline. So let's say cubic spline, and we'll specifically talk about that one. So cubic spline is a piecewise cubic interpolation. So that means interpolation by cubic polynomials. In a cubic spline, you actually interpolate between two adjacent points. You find a cubic polynomial between each pair of points. And that's because we're adding on additional conditions. So it's a piecewise cubic interpolation with the additional conditions that f prime and f double prime match up at each boundary, at each point. Okay? So unlike our polynomial, right, where we had something like this and something like this, in a cubic spline, what you would do is you would find cubic polynomials between each pair of points. So each of these is its own cubic polynomial. So 1, 2, 3, 4, 4 different cubic polynomials, one between each pair of points. And they're set up so that at this point where this cubic polynomial and this cubic polynomial join, not only do they match up in their y value, in their f of x value, but they match up at f prime and at f double prime, at the first and the second derivative. Okay? And so the first derivative implies that there are no sharp corners. The second derivative implies that there are no sharp changes of curvature, inflection points, so to speak. Okay? So cubic splines are a lot of work to get. There's a lot more conditions. They're very challenging to do. But they're very easy to do in Excel as long as you don't actually care about getting the equations. So if you do in Excel, if you do a scatter plot, and if you look at the scatter plots and curves in Excel, there's one where the points are connected by smooth curves. You'll see the button. What that does is it does a cubic spline interpolation between all of the points. And so you'll get a graph with a nice cubic spline interpolation. You don't get the equations, but you do get the picture, which is enough for this course. Okay? So the last thing that I want to talk about in this video, the rest of it we'll kind of go over in class, is that sometimes if you've got really noisy data, so data that looks something like this, you can't necessarily put a polynomial through all of this, or even like piecewise quadratic polynomials through this, because it's just really chaotic. But what you might want to do is find something that goes through kind of the main pieces of it and has the main features. Okay? So if you were looking for maybe like this curve, that kind of follows your data. Okay? So this is what's called heuristic interpolation. It's not strictly speaking a mathematical technique, but it can be very effective in getting some kind of model in data that's really, really noisy like this. So what we do is we choose reference points like the ones that I chose here that give us a general picture of the data. So basically what we're saying is, okay, if we picked out these 4 points, a curve through those 4 points would kind of give me all the main features of this model. Okay, it would follow my data. This is, like I said, this is heuristic. This is not mathematical. It's not rigorous, but it can give you a picture of kind of what the curve looks like if you're just trying to speak generally. Again, not with any mathematical precision. Okay? So what you do is you choose these reference points, and then through those reference points, rather than the original data, you find some sort of interpolation curve, whether that's a spline or quadratic interpolation, whatever you want to do, find that through those reference points rather than through the original data points. And that can give you an interpolation that doesn't get caught up in all of the noise and get really chaotic. Okay? So that's the topic of interpolation. We'll talk more about kind of some of the details in class.